G'day, in this video we're going to continue to look at properties of waves. Specifically, our focus will be on quantitative wave properties. In other words, ways in which we can take measurements of waves to describe them. This video focuses again on Module 3 Waves and Thermodynamics, Inquiry Question 1, which is looking at the properties of all waves and wave motion, but we'll be unpacking dot point 3 and 4. Which look at the measurement of waves specifically. We'll be looking at how we can represent waves graphically using a bunch of these different measurements and also complete some simple calculations using a few of these variables with some basic equations like the ones here. So our learning intentions today is to first define and actually use the measurements that we have to describe and quantify waves. We'll then also begin to apply wave concepts to those graphical contexts and complete some simple calculations using our frequency-based equations. So first off, there are 6 key measurements, 6 different quantitative ways that we can describe waves. I'm just going to go through each of them really quickly. They are frequency, velocity, wavelength, period, displacement, and amplitude. To visualize some of these measurements today, I'm going to be including a quick diagram up the top. So I'm going to draw a basic wave structure like this. Now, our frequency here refers to the number of wave crests which pass a point in 1 second. So one full wave motion might look something like this, from the bottom to the top, back down to the bottom again. We would call this one wave. And essentially the frequency is how many of these wave motions, like we've got here, pass a single point in a second. The symbol for frequency is F, and the units of measurement is in hertz. Sometimes you could use seconds to the -1 technically, but hertz is definitely the much more common version of that unit of measurement. The second one here, velocity, very similar to modules 1 and 2, represents how fast something is going every second. In this case, we're looking at the distance that the wave itself, or the energy within the wave, is able to travel every second. Its symbol is V, and the units of measurement, as always, is meters per second. Next, we have wavelength, and this is the distance between 2 successive crests. We could also reword that to the distance of one full wave. So in our diagram here up the top, if we have our 2 crest points, our 2 tops of the wave, the distance between them here would be the wavelength. And according to the symbol at the bottom, we show that as the Greek letter lambda. This is our wavelength, the distance essentially from one end of a wave to the very other end of one single full wave. The units of measurement is in meters. Next, we have the period, the time taken for one full wave to pass a point. So let's say that the wave was able to do one full motion in a second, or another way of wording that would be that one wave passes a point in a second. We would say then that the period is 1 second. Symbol is capital T, units of measurement is in seconds. Our next one here is displacement, and this is the distance a particle moves from the rest position. So this is more referring to the oscillation of a particle. So we could have a particle at a rest position, but over time that particle may eventually move. And the distance from the rest position would be our displacement. Now, there's no general symbol that we give for displacement. A lot of the time it just gets written out as displacement itself. You may see some pronumerals getting thrown around in different texts or different contexts. A lot of the time that kind of symbol needs to be defined because there isn't really a particular common convention for displacement. However, the units of measurement, as we would expect, is in meters. This other measurement, though, amplitude with the symbol A, is very closely connected to displacement, and it represents the maximum oscillation that a particle can have. In other words, the largest displacement from the rest point. Symbol again, capital A, and units of measurement M for meters. So with all of these measurements and our understanding of how waves behave, whether we're talking about longitudinal waves with their compressions and rarefactions, whether we're talking about transverse waves with their crests and troughs, we can begin to look at graphing either the behavior of the particles as individual particles or as a series of particles. The first graph that we can show is a displacement time graph. And this describes the position of a single particle over time. In other words, we're describing the oscillation of a particle. So I'm going to use my pointer to attempt to describe what this graph is actually showing us. So at time equals 0, we see that the displacement is also at the 0 point. But as time progresses, we start moving toward the crest, the very top of the graph. So as time progresses, we will see our particle begin to have a positive displacement. It will move, in this case, upwards. And then beyond that time point where the crest is, we see that there is a reduction in displacement until we hit the 0 point again. At this point, time has progressed to a place where we are now looking at this point here. Displacement continues to decrease though beyond the 0 point until we reach the time that is corresponding to the trough. At this point, we have a turning point where displacement begins to increase again, and the particle has reached its 0 point again. Essentially, we've gone through one full wave. And to visualize this one full wave, what we can do is sort of go through the whole motion. So from 0 point to crest, to 0 point to trough, to 0 point, we can see that my pointer here goes through one full oscillation. Again, crest, 0, trough, 0. However, we can also graph a wave by doing a displacement versus distance graph. And this kind of graph describes the position of a series of particles over a given distance. Now, this is best visualized in a transverse wave. And I'm actually going to draw over the graph to try and show what I mean. Here, if we were to show the behavior of a series of particles which are a part of a transverse wave, we could draw a series of dots and their respective displacements over the distance of a full wave. And so what we see is that as we move along this distance, at the beginning, the displacement of the particles begins to increase. And as we go further along with these particles, displacement then decreases to our trough, and then they begin to increase again to get to our 0 point. Essentially, what this graph does is plot out all of those particles and then connects the dots to make a nice wave shape. In a graph like this, we're able to quite easily see and visualize and measure out actually the wavelength, the distance between the beginning of a full wave and the end of a full wave. Conversely, when we're analyzing the behavior of one particular particle and we have displacement versus time, we're able to quite easily measure out the period. In other words, the time taken to do one full oscillation or one full cycle of the wave. Now, in the PowerPoint slides attached to this module and in the description of this video, I'm also going to be including a link to this video about how we can look at longitudinal waves and relate the behavior of particles, the areas of compression, and the areas of rarefaction in a displacement distance graph. Previously, we saw how easy it was to relate the position of particles in a transverse wave. When we start looking at longitudinal waves and compressions and rarefactions, things get a little bit more complicated. And for the sake of simplicity and time in this video, I'm not going to be including an explanation for that here today, but I do strongly encourage you to extend yourself and have a look at that video if you have the time. Now, for the last part of this video, I want to look at some simple wave equations. There are two that we're going to be focusing on in the waves and thermodynamics section of your data sheet. That is first V equals F lambda, which means the velocity or speed of the wave is equal to the frequency of the wave times its wavelength. And we also have F equals 1 on T. The frequency of the wave is equal to 1 divided by the period. What I would like to do is run through a couple of practice questions which apply both of these formulae, just so that gives us a starting point when we get into class and begin to practice them together. Something else to keep in mind is there are two relevant constants that are associated with these equations, and that is the speed of sound in air as well as the speed of light. These are both values that can be substituted into the V equals F lambda equation because it's associated with the speed of the wave. So if you are told in a particular question that requires V equals F lambda or involves frequency, wavelength, etc., if you're told that you are working with sound or light, you can just automatically assume, unless told otherwise, the speed of either the sound or the light and substitute those numbers straight in. So for the first question I have today, it actually involves a sound wave, and we are going to need to use our data sheet to support us. We're told that the particles in a sound wave complete one full oscillation in 0.0050 seconds, and that we need to calculate the wavelength of the sound wave. The first thing that I'm going to do is create a data column to help me solve this question. Now, we've been told that the sound wave will complete one full oscillation in 0.0050 seconds. If we're looking at the time to complete one full oscillation, we are looking first at the period of the sound wave. This is capital T. I'm also going to identify that we are being asked to find the wavelength of the sound wave, that's lambda. And because we've been told that we have a sound wave, we know the velocity of the sound wave, and that, according to the data sheet, is 340 meters per second. In our data sheet, we do not have an equation which relates the period, the wavelength, and the velocity of sound, but we do have two equations that we can use in conjunction with each other. First off, we have F equals 1 on T, and we have V equals F lambda. So using these two equations, we can calculate for the wavelength as long as we know the frequency, and we can calculate the frequency given the fact that we know the period. So knowing that my period was 0.0050 seconds, I was able to calculate the frequency to be 200 hertz and substitute that into a rearrangement of our V equals F lambda equation to calculate for lambda our wavelength, which is 1.7 meters. That answer is being given to two significant figures, given that both the velocity of the sound as well as the period are both written down to two significant figures as well. In our second question, we're going to have to work the other way. Here we've been told that a wave is generated in a rope at a velocity of 2.1 meters per second, and that if the wavelength is 0.34 meters, we need to try and find the period of the wave. Let's start first with a data column and identify our relevant equations. So from the data that we've been given, it's pretty obvious that V equals F lambda is going to be particularly useful to us. However, we've been asked to find the wave's period, not its frequency. So once we have its frequency, we can rearrange our F equals 1 on T equation to calculate for T. So for this solution, I first rearranged V equals F lambda to make frequency our subject. That then allowed us to substitute and calculate for frequency, that is 6.176 hertz. What that actually means is that there are 6.176 full waves generated by the rope every second. Once we have that frequency, we can then rearrange and calculate for T, the period. That gives us 0.16 seconds. And what that means is one full wave in the rope is completed every 0.16 seconds. Note that I gave my answer to two significant figures. And again, that's based on the data that we used from the very beginning. All the data given in the question was given to two significant figures as well. Thank you very much. In the next video, we're going to start moving on to inquiry question 2 and start to look at how waves actually work and how they interact with the world and how they actually behave. The remaining 3 inquiry questions that we've got to look at, inquiry question 2, 3, and 4, will start to look at specific types of waves, what they do, how they interact. The next video will be the start of that. Until then, have a good one.